In a galvanic or voltaic cell, we're looking at a spontaneous chemical reaction that will give us electrical energy, such as a simple battery. And since a galvanic cell is a voltaic cell, we can use the two interchangeably. To understand how batteries or galvanic voltaic cells work, we first need to review a few basics. Detailed videos for the galvanic or an electrolytic cell are available on my website linked below, or go to leahforsyth.com/electrochem. As a reminder, redox is a pair of reduction and oxidation reactions, which gives us a flow of electrons, and the mnemonic, Leo the lion says, grrr, tells us that loss of electrons is oxidation and gain of electrons is reduction. If redox is happening in a contained environment, for example, A has an electron that moves over to B, we can't capture it. But if A and B are separated and that electron is forced to travel over the wire, we now get a current on this wire that we can harness for electricity, for example, to power a cell phone or a light bulb. So yes, we can have redox outside of a battery, but if it's self-contained and we don't capture it, what's the point? The key to using this energy is to force the electrons to flow over a wire or force them to flow over something that'll capture the current. And how do we do that? By breaking the reaction in half, as discussed in the redox reactions video linked below. A complete redox reaction can be broken down into two half reactions. For example, the spontaneous reaction between zinc solid and copper ions to give us zinc ions and copper solid. If allowed to react in a container, the electrons flow from zinc to copper, and we get nothing out of it. Breaking the reaction in half, the two half reactions are as follows. Zinc solid goes to zinc 2 plus 2 electrons, and copper 2 plus 2 electrons gives us copper solid, where the 2 electrons that come off the zinc solid are captured by the copper ion to form copper solid. And how do we harness the electrical energy? This brings us to the setup of the galvanic or voltaic cell. We start with two separate containers, each one called a half cell, because together they make up one galvanic or voltaic cell. Each half cell has a metal electrode that is made up of the metal that we're either forming or breaking apart. On the left, the electrode is zinc solid, and on the right, the electrode is copper solid. Each cell also contains a solution with the ions of that metal. But metal ions can't exist by themselves, so the solution will be made up of something like zinc sulfate, which has sulfate as a spectator ion to balance the zinc 2 plus. Same thing on the right with copper sulfate, where we have the copper ions balanced with sulfate. I only put one, but obviously we have millions and millions of ions equally balanced in solution. And now the reaction can happen. Electrons should... Wait a minute. Electrons can't flow because we have to connect them. The two half cells are connected by a non-reactive metal that can conduct electricity between the two electrodes. Now the electrons can flow. If you look at the half reactions, you'll see that zinc solid is losing 2 electrons. The electrons are coming off. And copper 2 plus is gaining the electrons. The electrons are flowing from zinc to copper. The way that happens is one of the zinc solid atoms sitting on the electrode will give up 2 electrons. The electrons will go up the wire and travel all the way to the copper cell, down the electrode and into solution. Let's look at what happens to each one. When a zinc atom breaks apart according to this half reaction, we have a zinc solid turning into a zinc ion. The ion will no longer stay on the metal, but instead that ion will now join the other ions in solution as the electrons travel up over the wire and towards the copper. The electrons don't sit on the copper though, because the copper is solid and has all the electrons it wants. Instead, it travels down the electrode towards the solution and attracts a positive ion. When two electrons attract and ultimately connect with a copper 2+ ion, that copper 2+ plus two electrons will form a copper solid. That ion is now out of solution and sits as another atom on that copper electrode. As this continues to happen, more and more zinc breaks away from the zinc electrode, more and more electrons travel over the wire, and more copper ions will come out of solution and grow onto the copper electrode. The zinc electrode is called the anode, and the copper electrode is called the cathode. They're specifically named for the reactions that happen at the electrode. Since zinc is losing electrons, it is undergoing oxidation. The anode is the site of oxidation. The copper ions are gaining electrons. That means they're undergoing reduction, which means the cathode is the site of reduction. To help you remember this, just think of furry animals. An ox and a red cat. An ox tells us that anode is the site of oxidation and cathode is the site of reduction. Another thing to recognize is that the anode is negatively charged and the cathode positively charged. And the way I remember this is that an means without, means it's negative, and cathode, that T, looks like a positive charge in the word. This changes slightly for an electrolytic cell, which we'll actually look at in the next video. If you think of the charges logically, it makes sense. Electrons are negative, and like repels like. The negative electrode will repel or push away the negative electrons. But the cathode is positive, and since opposites attract, the negative electrons are attracted to or pulled towards that positive electrode. As you'll notice, the electrodes themselves are changing in shape because every time zinc loses an atom, the zinc electrode gets smaller, and every time copper gains electrons, the copper electrode gets bigger and bigger as more solid is adding on to it. Are you with me so far? If yes, make sure to give this video a thumbs up, subscribe to my channel, and then hit the bell icon so you don't miss out on any new videos. But wait a minute. If negative electrons are constantly moving from the left to the right, won't the solution on the right become very negative and the solution on the left become very positive as the negative electrons leave? This cannot happen for two reasons. One, chemicals like to move down the gradient. Electrons are not going to go towards a solution that is already negative, and they're not going to leave a solution that is very positive. And two, a solution can't actually exist as negative or positive. Anytime you have a negative ion in solution, you have some spectator cation balancing it. And anytime you have a positive ion in solution, you have a spectator anion to balance it. And this is accomplished with a semi-permeable membrane called a salt bridge. But it doesn't have to be anything fancy. When we set up a galvanic cell back in chem lab, we used 2 styrofoam cups for the cells, and then a rag soaked in good old table salt, or was it KCl, and that acted as our salt bridge. Here's how we maintain the flow of electrons in this cell. Every time we have an electron flowing from the anode to the cathode, we have a potassium ion entering the cathode solution, and a chloride ion entering the anode solution. Some professors will teach this balance of electrons as the actual spectator ions moving. For example, showing sulfate from the solution that is getting more negative, moving over a semi-permeable barrier towards the solution that is getting more positive. Just make sure you pay attention to the charge, because sulfate is -2, so every 2 electrons entering the copper solution would cause 1 sulfate to enter the zinc solution. Let's say you want to show what is going on in the cell, but you don't have the time or patience to draw the entire system the way I have here. All you need is a cell diagram. A cell diagram is a written representation of exactly what is going on here. For each half cell, we show the half reaction as a reactant followed by product. with a single line in between to show the phase barrier, separating the zinc solid from the zinc ions. Same thing for the right, reactant first, then product, so copper 2 plus, a single line separating the copper solid. We put 2 lines in between to show the cell boundary, meaning the separation between the 2 half cells, or to represent the salt bridge. And yes, it does matter what is on the left and what is on the right. We need the anode as the first reaction and the cathode as the second reaction. If you look at a table of redox potential, you'll see that the reaction we showed here is a spontaneous reaction. Copper has a much stronger desire for electrons, and when copper and zinc are forced to fight over an electron, zinc will give it up to copper. But what happens if we have a non-spontaneous chemical reaction? If this is the kind of reaction that powers your cell phone, what do you do when your cell phone runs out of battery? How do we force the electrons to go backwards? That's where the electrolytic cell comes in, which is exactly what we'll cover in the next video, using the link below, or go to layerforsci.com/electrochem. The link again, layerforsci.com/electrochem.